Okay, so the matrix transformations. M is given by 0, 2, minus 1, 0. The diagram is printed onto book there, shows the unit square, the image of the unit square, and the transformation is this new thing. Draw and label O, A, B, C, indicating clearly the coordinates of A dash B dash C dash. Okay. I did this with my I still got the crayon with my unit square thing. So let's actually do that multiplication. That's 0, 2, minus 1, 0 times. What would our unit square look like? Well, our unit square would be there's 0, 0. I'm not sure we really need it. There's A is 1, 0. B is 1, 1. C is 0, 1. I'm being careful that I'm getting these in a sensible order, and in fact, this is all. There we go, that was much more fun than it should have been. Here is O, A, B and C. So I'm being really clear about which point is which as I multiply it. As I multiply it, obviously 0 is going to go to the same point, and the clues in the question, they've already put it on the same point. So we've got, have I lost the top of the page there as well? As we do this then, we've got 0 times 0, yeah, 0, 0. Right, so look at A, we're going to 0 times 0 plus 2 times 0, and minus 1 times 1 plus 0 times 0. So we've got the new coordinates of A is 0 minus 1. B, 0 times 0 plus 2 times 1, minus 1 plus 0, gives us a minus 1 there. C, 0, 2, so that's 2, and minus 1 times 0, and 0 times 1 gives us 0. So they are our new coordinates. So these points here, this is the new A, the new B, and the new C. So I'm going to really carefully mark those points on my diagram. I did this bit of working out. So the new A is 0 minus 1, 0 minus 1. There's my new A. My new B is 2 minus 1. There's my new B. And C is 2, 0. There is my new C. And there is, the ruler probably, the image of my new shape after the transformation. Okay. It did say label and indicate clearly the coordinates. I think it's probably clear enough from my matrix, but just to be certain, I'm not taking any risks with this. So these coordinates are 2, 0, these coordinates are 2 minus 1, and these coordinates are 0 minus 1. There we go. We definitely are going to get all 3 marks for that. Part 2. The transformation represented by M is equivalent to a transformation P followed by a transformation Q. Give geometrical descriptions of a possible pair of transformations P and Q and state the matrices that represent them. Right? So let's think what has happened to this. Well, having drawn it so well, I hope it's reasonably clear what's happened to this. It looks like we have rotated it 90 degrees clockwise about the origin, and then we have stretched it scale factor 2 in the x direction. Does that seem reasonable? That's kind of jumping out to me as being what's going on with this. So we have a rotation 90 degrees clockwise about 0, 0, and we also have I'm going to need a space to put the matrix in there, we have a stretch, not an enlargement, it's a stretch, isn't it? Scale factor 2, and we are in the x direction, so parallel to the x-axis. Okay, we're making sure that our description is fairly solid about what we're doing with this. So what about the matrix? Well, a rotation 90 degrees. In the formula booklet, we know this, don't we? If we haven't learnt this, if we haven't got this memorised, then we can always fall back on the formula booklet where it says an anti-clockwise rotation through theta about 0 is given by that matrix. So we are wanting that matrix, we maybe have remembered this anyway, but we're wanting the matrix cos theta, cos, what would it need to be? This is anti-clockwise rotation, so we're going clockwise, so it's minus 90 degrees. So cos minus 90 minus sine minus 90, sine minus 90, cos minus 90. And we need to put it not in terms of trig functions, we need to turn it into an actual thing. Cos of minus 90 is 0, isn't it? Sine of minus 90 is minus 1. That's right, isn't it? So minus that is going to give us plus 1 there and minus 1 there. So there's our first matrix. We're going to do a check of this in a minute anyway. And then we've got a stretch scale factor 2 parallel to the x-axis. I don't know if have we remembered this. This is maybe one that we should have learnt. We know that just an enlargement, you would take the identity matrix and you'd multiply the diagonals by the thing, so that we know that they stay as 0. If it had been enlargement, it would have been both of them we'd increased, but because it's parallel to the x-axis, we're only going to increase that one. So that's the matrix that we have. Now, we can check this, can't we? Because if this is right, and it's a tiny job to check this, if this is right, and we're doing, we're saying that this is P followed by Q, so this is P, and this one is Q. If we're saying it's P followed by Q, then the overall thing, you write that as being P followed by Q, is what the matrix should be. So that should have been our transformation matrix. So that means 2, 0, 0, 1 times 0, 1, minus 1, 0. That should give us the matrix we started this question with. 2 times 0 plus 0 times minus 1. 2 plus 0. 0 minus 1 and 0, 0. And was that what we had? 0, 2 minus 1, 0? Yes, it was. So we were right. So we can be convinced that we did this in the right way. Even if our descriptions aren't perfect, we definitely got the right pair of matrices for that. There we go. And that's the transformatory power of matrices.